So let's quickly see how we do these projections onto a lower dimensional principal component space in MATLAB. Okay. So let's say we have this original data set, m dimensions, n data points. In the example that we just saw, n was 60,000, m was 784 dimensional. And then just like before, we take the covariance of this, which will be m by m, in other words, 784 by 784. And then we compute the eigen values and eigenvectors, reverse the order to get the eigenvector matrix such that the first column is the first principal component, the second column is the second principal component, in other words, has the second largest eigenvalue, etc. The eigenvalues corresponding to these eigenvectors are in decreasing order, going from left to right. Now, let's say we want to project the full data onto the first few principal components. Okay. Let's say we pick the first k principal components. It could be 10, it could be 100, depends on the data set, depends on how accurately we want to approximate the data. Let's say we pick the first k principal components, and then so we basically define this matrix U, which is V, all the rows, and then just the first k columns, which gives us the first k principal components. And what we want to do is project every data point. Every data point is every row of P, or the original data set, onto the top k principal components. But we want to do this projection after mean subtraction. To do that, we take the original data matrix and go minus mean P. P itself is n by m. And then mean of P, if you do that in MATLAB, will give you it will actually give you a 1 by m matrix. This is a typo here. It should be 1 by m, not n by 1, I think. But then if you do the subtraction, MATLAB essentially subtracts this 1 by m matrix from every row of P. So every data point has the mean subtracted. MATLAB does that automatically, and then Q will now be also an n by m matrix, where each row is the mean subtracted version of each row of P. So this is the mean subtracted data. So if you plot Q, it'll have mean equals 0. The projection onto U is just R equals Q times U. That's as simple as that. We project each data point onto a column of U, each data point onto a column of U. So it's just matrix multiplication, right? And you get, again, n rows because we have n data points, but then we only get k columns because U only has k columns. And we've essentially taken this m dimensional data to a k dimensional data here. That's what we've accomplished, okay? So instead of the data set having n by m numbers, it will now have n by k numbers. And this is what we mean by reducing the dimensionality of the n by m data set. We've reduced it to n by k data set. And if k, namely the number of principal components, is much, much smaller than m, then we've achieved a big reduction in dimensionality. Okay, this is basically one way of compressing data, basically because we've reduced the data that we're dealing with from essentially m to k, and this would be called lossy compression, as we are approximating the original data set n by m with n by k. And it's an approximation. We are throwing away some stuff in the data. It's not going to be perfect, as we clearly saw in the demonstrations. So it's what would be called lossy compression. Lossy meaning there is some loss in the data. But if the approximation is good, the loss can be pretty small. Okay. And as we discussed already, if k is much smaller than m, this is a good compression. There may be some compression algorithms that actually rely on doing principal component analysis, where you compress the size of your file, size of your music file, size of your video file. You can use a method like this to do image compression or video compression and so on. Okay, so that's how you go from the full data set to the compressed data set or dimensionality reduced data set. What if you want to recover the original data from the compressed data? The compressed data set is R, the original data set is P. You just describe how you go from P to R. If you want to go from R to P, you want to basically reverse the process. You want to construct the analog of Q and then the analog of P, basically by reversing these things. And that's what I've described here. If you're given R, you can construct Q bar, which is not Q, but it's an approximation of Q, projection of Q onto basically these principal components, which is going to be R times U transpose. It's not U inverse because U is not a square matrix. It's going to be U transpose. And then we can construct P bar, which is going to be an approximation of P. Basically, it's going to be a projection of P onto this subspace, which is going to be Q bar plus mean of P. Okay, and P bar is the reconstructed version of P. It's going to be what we would call low dimensional projection of P, and this is what we actually plotted when we did this. When we ran this thing, what we have plotted here is a particular row of P. What we are plotting here is the corresponding row of P bar, which is obtained by reconstructing the image after projecting onto 45 principal components or 46 principal components and so on. We project to the principal components and then project back up. One doesn't call that project, but represent that back into full dimensions, and you get this. Okay. So this is a row of P, this is a row of P bar. And this is the sense in which P bar is an approximation of P. Okay, so that's how you project back. Notice that this projection back actually requires not just R, but also a couple of more things. For instance, we need the U matrix. We also need mean of P. So to do the reconstruction, we need R, we need mean of P, and we need U. So the data compression is not as great as going from M to K, in other words, N by M to N by K, because R is not the only matrix that we need to store. We need to store R matrix, but also we need to store the mean of P matrix and the U matrix. So in the compressed form, the total numbers is Nk plus M plus Mk. In the original data set, the total numbers would be N times M. So the compression would be the ratio of these two things. For something like MNIST, you can put in numbers here. If we say M equals 60,000, M equals 784, and we use about 20 principal components, the compression that we get is, I suppose, order of 40, I suppose. Okay. But higher N, if you make N bigger and bigger, you will this thing can become larger. Also, I suppose once N is large enough, the main thing that matters is M over K. So 784 by about 20 maybe is about similar to what we have here. So it looks like with about 20 principal components, we were approximately able to figure out what the image looked like. Maybe not nearly perfect. Maybe with about 200 PCs, it would have been better. So it depends on how much compression you want. With 200 PCs, you'll get maybe a compression factor of about 5. With 20 PCs, looks like you get a compression factor of about 40. So I guess it depends. Okay, so let me say a couple of more things. One useful implication of dimensionality reduction is that we may be able to solve much smaller machine learning problems, right? So instead of dealing with 784 numbers and these very large matrices, we may be able to solve, I don't know, 20-dimensional problems or 200-dimensional problems instead of 1,000-dimensional problems. So that is one potential advantage. It might work on some problems, although if you do use PCA to project down, you may not be able to use sort of convolutional networks because you sort of corrupt the notion of neighborhood pixels and things like that. And I'm just making a brief remark here that PCAs have been used in fluid mechanics, biomechanics, robotics, many other sort of classical engineering fields. Very useful. We'll have a homework problem on this. Before we sort of stop talking about PCAs, I'm just going to show one last demo, which really just walks through this projection and back. Loading MNIST, doing the PCA with eigen decomposition here, reversing the order of eigenvalues and eigenvectors. We're just using the top 20 PCs. And then here, I'm actually just doing the projection, mean subtraction of the full data set. And then this is the projection onto the K-principal components. And what I'm doing is storing all the necessary data into a strut called reduced data. So let me just run the whole thing. Takes a few seconds. So I suppose we have this variable called reduced data, which is 60,000 by 20 numbers, 784 by 20 numbers, and 1 times 784 numbers. And then the original data set, of course, is size train X, which is 60,000 by 784. This would be the compressed data. So if you're imagining data compression, this is the original data set, and this is the compressed data set. And you will notice that this is, I don't know, 40 times smaller or something, like we just saw. Okay. So that's it for PCAs. Maybe I will just spend a couple of more minutes talking about extensions of PCAs or analogs of PCAs in the neural network world. PCAs are very classical. They're just using eigen decomposition. We can use, but unfortunately, they're restricted to finding these linear planes or linear surfaces, essentially, right? Because that's what they're built upon. Like we are looking for vectors along which variances are maximized. So all they can do is find these linear subspaces or linear affine spaces. If you want to, let's say, approximate data that is more nonlinear looking, like let's say the data is arranged in a curve, then we can use something called autoencoders, which maybe I'll talk about in the next small video.